Okay, the formula that we derived last time is up here on the board. On your formula sheet, it's formula number 14. Talks about the Laplace transform of what we get if we turn on, at time a horizontal translation, a units to the right, of some function y of t. And what we get is just the Laplace transform of that function y of t multiplied by e to the negative as. But there's a lot going on in this formula, and very often we're going to be able to use that formula, but we're going to start with something that's not quite a perfect match. So we have to manipulate it a little bit first to make it a perfect match. Okay? So that's what I want to look at here. So basically in this video, we're going to practice using the formula in this direction, starting with a function y of t, taking the Laplace transform to get the corresponding function of s. Then in the next video, we'll try working in the opposite direction, taking inverse Laplace transforms using this same rule. So I've also just written up here the Laplace transform for e to the at. That was rule number 1. That's the other formula that we've derived at this point, so we'll be using that one as well. Now, in a minute, I'm going to suggest that you pause the video and try to work these problems out on your own. Before I do that, I want to just point out that neither one of these problems is an exact match, because I need to have the same number a in both of those positions, and I don't have that in either one of these. Now, I could just use the definition of Laplace transforms and evaluate that improper integral. That's the hard way of doing this, okay, and definitely the long, tedious way. What's going to be simpler is if you do a little bit of algebra to rewrite these functions first to try to make them a perfect match here so that you can just plug into this formula. Okay, so go ahead, pause the video, try to work out these two problems, then come back and we'll work through them together. Welcome back. Okay. So if I'm looking at this, this tells me that my a is 2. That's the time I'm turning things on. Can't really mess with that. That means that I want this to be a function evaluated at t minus 2. Right now I've got 2t minus 4. Looks like a simple factoring will do that for me. So I can rewrite this as the Laplace transform of mu sub 2 of t e to the 2 times t minus 2. Now I've got t minus 2 and 2 here. That's looking good. What that tells me then is that my y of t, the function that I've translated, is e to the 2t. Okay. So, according to this, I can now use rule 14, and I can say that's going to be e to the negative 2s times the Laplace transform of e to the 2t. Now, I could go straight to what this is. I find it actually helpful to write down that that's the function that I'm transforming, because that's not what I see when I look over here. Okay. I also found it helpful to explicitly write out what a and y of t were here, because I like to see what the formula is that I'm transforming. Now, if you're comfortable looking at it here and going right to what the Laplace transform is, that's okay. All right, so this would be e to the negative 2s times, this is the Laplace transform of e to the 2t. So in this formula, this a, which is different from that a, okay, is 2. So I'm going to get 1 over s minus 2. In other words, e to the negative 2s all over s minus 2. So that's our Laplace transform for that first one. Okay. Now the second one I think is kind of interesting, because if I look at this, at time 3 I'm turning on e to the t. But that's not a horizontal translation of e to the t. That's just e to the t. So if I turn this on, it would pick up at time 3 at e cubed, not at e to the 0. Perfectly legitimate, but it doesn't match this formula, so I can't use formula 14 at this point. I don't want to just have to work out by the definition of the Laplace transform the improper integral, so I'm going to try to rewrite this. Again, pretty clearly my a has to be 3. I can't really mess with that. So I want to rewrite e to the t as some function of t minus 3. Well, how about this? 3 plus t minus 3. That's a fancy way of writing t, and there's my t minus 3. Now notice, because I'm adding in the exponent position, that's just e cubed times e to the t minus 3, and that's just a constant. And Laplace transforms preserve multiplication by constants. So I'm going to rewrite my function this way. So I'm going to say this is the Laplace transform of mu 3 of t times e cubed e to the t minus 3. And that's telling me that my y of t, the function that I've shifted 3 units to the right, is now just e to the t. I didn't actually want at time 3 to be at e to the 0, which is 1, but I'm not now because I'm multiplying by e cubed. So that puts me at the right place, but that allows me to write this as a match for this. So now I can go ahead and use formula 14. I think I'm just going to bump over here as I do that. So I'm going to get, by formula 14, e to the negative 3s, here. And then I'm going to have the Laplace transform of e cubed times e to the t. That constant times the function that I'm shifting. I'm not taking the Laplace transform of e to the t minus 3. I'm taking the Laplace transform of e to the t times e cubed. Okay, so this is e to the negative 3s times e cubed, Laplace transform of e to the t. And that's just e to the 1t, so that's going to give me 1 over s minus 1. So I'm getting e to the negative 3s times e cubed times 1 over s minus 1. If I want to, I could go ahead and combine those and add those exponents. I probably would actually just keep it in this form though, because e cubed is just a constant. And I know if I were to take an inverse Laplace transform at some point later on, I can factor out that constant. So I'd probably prefer to leave it in this form.